Okay, here we go for PLC 3, week 3. We're going to call this remote I/O. We've already done some of this in program controllers 2. We're going to get back into it a little bit. So welcome. I'll take a look at your attendance, keeping track of that on the D2L and in class. And then we have new handouts. I'm giving everybody handouts as we go. Some of them get updated a little bit as we go. So hopefully you're getting the handouts and I'm posting them on the D2L as well. So we're going to start with our week 2 lab review. And it says, we converted the car wash to get back into Logix, with all our subroutines and mapping of I/O and system bits and all that kind of stuff. And so, the bottom line is, did the car wash work? When you're refitting an old system, which doesn't happen that much anymore like it used to. A lot of systems are brand new. They're designed for the PLC. Sometimes you still refit it, though, take a hardwired and then refit it to a PLC. The bottom line is, did it work like it used to? And so there's a lot of different options, and there was a lot of different options of how you wanted to do this. And so, maybe it worked better, maybe it didn't work as well. Hopefully it worked as well, right? And so, what unique items did you add? Some of the unique items you might have added were obviously more safety, depending on what level of safety you wanted. You had system bits, safety contactors, incorporation of your safety relay for your master control relay, monitoring of the process. All these questions we'll dig into a little bit here. But once again, the bottom line, did the car wash work? And as everybody did it, everybody's car wash did look just a little bit different. And so, hey, that's what you're going to get, but you're just trying to figure out if it worked or not. Okay, so we talked a little bit about stop categories last time. So where the machine stop should remove stored energies in the systems or bring it to a stop. And there was 3 categories of stop. And we were talking about category 0 stop because we didn't have a PowerFlex 525 that we could bring this to some type of a controlled stop. We were just like a category 0 stop where we had an uncontrolled stop, and that's what we were using here. But there's different stop categories depending if you want to control the stop and then even remove all the power to the unit after the controlled stop. Okay. And then we talked a little bit about, the category 0 stop. And not being the disconnect, we had a little homework problem with that, and people did put the disconnect. But, when we say stop, we're probably not talking about the disconnect. We talked about it could be the memory circuit, or you could even incorporate a safety relay, a single channel or 2-channel e-stop to accomplish a category 0 stop. So as we take a look at our category, let's go level 0 stop. Let's just take a look. I think I asked for the homework. One was with a safety relay, one wasn't. So if we're doing it without a safety relay, we're probably just going to do the old-fashioned stop. And let me put 2 of these in series like this, and we'll talk about stop, start, and then we would do a start, and then we would do a CRM, and then we would put that hold contact here, right? And then I always like to put like an amber light or something to indicate that the master control relay is on and that you can electrocute yourself. So if this is what you're doing, this could be a level 0 stop without utilizing much else. It's going to be an uncontrolled stop. So this would probably be just the simplest way to do it. Now, I put 2 stops here. So when we see multiple stops here on a CRM circuit, you're thinking that there's multiple places around the work cell, at the front of the work cell, at the back of the work cell, on the left of the work cell, wherever, where you could hit stop and kind of kill the system. Absolutely. Or when we talk about using safety relays and dual channel safety and all this kind of stuff, you're talking about dual channel e-stops. This is a single channel e-stop, but I guess you could take this contact block and put it onto here to make this a dual channel, and then just run one of the stops back through the other contact block, and then farther on, so that when I hit this, I would break both contact blocks here of this. Well, that's not really what we're talking about, but if you're worried about, some type of a welding operation of these stops, you could, I guess you could put a dual channel stop there. But usually with the older memory circuit kind of master control relay, and then once again, here's your CRM, bringing power to the rest of the system. Yeah, that's really not what we're talking about here. Now, when we get to, a safety relay, that's where we get to the dual channel. And so when we had 11 and 12 here, remember we could have, a stop button here, and that would be a dual channel e-stop, a dual channel e-stop here, that when I push that, it would break that. And if you wanted multiple e-stops around the work cell, well, they're not going to be just single channel e-stops. These are going to be all two channel or double contact block e-stops around here. And you could do a few of these around the work cell to stop it. Okay, and remember, sometimes these might, you know have a dotted line around there to indicate that they're a single unit, right? Okay, and then if you wanted even more safety, remember, this could go to, another set of, safety rated contacts or something, or it could go to, safety gates, and you could have this huge safety circuit that then wraps back around there, that if any of those get broken, any of the two channels get broken, or even if the single channel gets broken, the relay goes down. Okay, so when this was talking about some type of a zero level E stop, that's probably what we're talking about. And then for the reset here, if you wanted, what we're doing makes it just simple for us to see, is that is a reset button. But same thing here. This could be some type of a contact right here that's going to close if the gate, if you shut the gate, or you reset a relay or something like that. So, but we've just been going with some type of this like this. Okay, and then for the monitoring, the simplest monitoring that we could do is just go like this and just say, just make it close like it normally closed. And then we're kind of in business here, and because we've got, a simple stop, and then, whatever we're doing here, we're bringing voltage through here, and then that's going to, some type of a contactor, K1, and that is using a safety relay to make just a real basic e-stop. And I'll say it again, that the safety relay here brings down the contactor, okay? So it brings down the machine control, which then controls the motor. And so once again, just for to go over it, somebody, sorry, they put a disconnect here on their motor. They called this a disconnect, and I got the wrong symbol there, sorry, but a disconnect, and they put that as their level 0 e-stop. Well, it's not really, it does remove power to the device and to everything, but when we talk about stop, we are hoping to see, some type of a stop button or emergency stop button. Okay, so that's something to talk about. Now, we'll talk about the safety relays again here for a few minutes, because we're doing pretty good with them, but just want to throw around some ideas, because there's so many variations of what you can do here. I posted those documents on the D2L. Man, that's great reading. You should read all those documents and take a look and see what's going on, just because to see what all the options are. So on the safety relays, the redundancy is important in safety relays and the safety systems. Why do one when you can do two and spend more money and get more wiring, right? And remember, the safety relay is part of the safety system. The way that we're hooking this into the PLC is not part of that safety system. It's just monitoring the system, but it's not part of the safety system. Okay, these relays and contactors, safety contactors, and everything that we we talk about our using positively guided contacts or force guided contacts where they're all open or they all close. You can't get some partially open, partially closed. The monitoring the state of devices. So we use those safety contactors, and we wired the normally closed back through here so that the safety relay was monitoring the contactors. Or if you have safety relay and door switch or other outputs or whatever, everything can be kind of monitoring the status of each other to be sure that everything is working like it should. So there's a lot of monitoring that goes on, and that monitoring can be of the safety circuit, okay? The PLC monitoring, we've got that going on as well. But remember, the PLC is not necessarily part of the safety system here, okay? So when we do the PLC monitoring, are you using the normally open or are you using the normally closed? And so that's what we have right here. We have the input module, okay? And the input module is sunk, right? And so you've got a channel coming into here, into input 1. That's my PLC in. Well, are you using the closed ones here? You know, are you bringing the voltage into here, into closed, or are you bringing the voltage into open? And then, you know, is it coming, you know, through there or through here? Well, it kind of doesn't matter. You can do what you want to do because this PLC is not going to kind of fail safe the way that an e-stop does. This has to be turned on and activated for these items to close and for these to open. And so if you use these, then you're going to program it, you know, because they're going to be closed. And then you're going to say that the PLC would, or the safety relay would go off and they would open, okay? And then your ladder logic can just be like this, right? This could be the safety relay contact, okay? And so when this would be going to my PLC, my ladder logic, so that when this is on, you know, this is true, and then my safety system's on, and I can do my system bits and all this kind of stuff and go. Or if you wire it through the closed, you're going to have a close because it's going to start as closed, and then when you energize everything's good here and it comes on, these are going to close, and then this is going to be no longer written as true. It's going to be false, okay? And then same thing if you lose power here, then it goes back. So you just have to examine the logic the same. Now the thing that's kind of interesting about this, or kind of weird to think about, is that this doesn't monitor this. This is going to have a hard time monitoring the status of a wire if you lose a wire. So if the safety relay is working like it should, remember that is directly controlling the device, which is good. It doesn't matter what the PLC does. If we kill the safety relay, this is going to come down, and the PLC program could keep running. It doesn't matter. This is not going to run right here. But what if this wire falls off right here? Let's say this wire falls off out of the PLC right there. Well, that doesn't affect the operation of the safety relay. We can still directly bring down the motor controller right here. But depending on how you program this, if it was open or if it was closed, which once again, it's not part of the safety circuit, you know, this is controlling that. But if we lose that wire, it may or may not bring down your PLC system bit or your PLC logic that you got going here. So that's kind of something to think about. But if you want to do this oppositely and try and plan for, you know, the loss of a wire falling out here, well then that doesn't. It seems illogical, or it changes the way that, you know, your PLC program works. It still works. The moral of the story is, if this is, you know, open, close, it's all the same. You're probably not going to do a very good job of accounting for the wire falling out of the PLC, because even if this did fall out of the PLC and it killed the PLC program, that doesn't mean that you killed the contactor, because the contactor is controlled by the safety device. They're separate. So hopefully that little discussion is making sense. You just want to have the safety relay doing what it does, and just have the PLC monitoring it a little bit in doing what it does, okay? System bit. So that's what we were talking about, monitoring the safety relay with it normally open and normally closed. This monitoring is not part of the safety circuit, okay? But you probably, most of all of you did, is you had some kind of a system bit, and I like that. So somewhere here, you had, if you had a start on it, like if you had a PLC start, and I'll call it PLC start, something on the PLC, a push button that would bring in a system light, and the system light is okay. We can dedicate an output for a system light so we know it's on, or you could call it system bit if you want and turning on a light. And then you got a system light here, right? And then your system light is used on all of these contacts here, later in the program, almost like the MCR functionality. You got to have that on. But then what you did right here is you put your safety relay contact, and whether you had it switching to become, whether you had it switching to become closed or had it switching to become open when the safety relay was reset, would be whether this would be XIC, XIO, examine on, examine off. So, but that's good. If the safety relay goes down, that killed the system, which did kill all of the program. But just I hope you understand that if you lose the wire falls out of the safety relay that's going to the input of the PLC. This might not immediately bring it down. If you program this the opposite way, it would. But at that point, killing the safety relay would then do the opposite of this if there was no wire there and it fell out to begin with anyways. So it just doesn't matter whether it's open or closed or open. You want to give that some thought, and I can explain it more in class and draw the two different scenarios if you want. So now we got your safety relay control, and what I'm talking about, the safety relay is the direct control of the field device, regardless of what the PLC thinks it's doing. If you hit the safety relay, the field device is dead. The PLC could just be blinking away, having a great grand old time. Your system bit may or may not have come down, but it doesn't matter. The safety relay has broken the control. So the question becomes, do you want to do the individual device, or do you want to do the entire output card? And then there's a couple of ways to think about this right here, okay, because you're going to see them out there. So if I go back to this right here, and I'm going to focus on this CRM right here. Let's go back to the master control relay. If the safety relay brought down a master control relay, let's call that a CRM right here, okay? Basically what we're doing with our master control relay right here is we are putting the safety relay contact right here, safety relay contact right there, 13 and 14, okay? So that if the safety relay gets hit, that brings down the master control relay, and as we know, this voltage right here, this goes to the input and output modules, or the field devices, and it sources the output module. So if you have your output module here, and it's a direct, voltage source into it, and the voltage goes down, well, then your outputs are dead. And we brought this down by bringing the master control relay down. Okay, nothing new or nothing fancy that way. Brought the CRM down, brings down the voltage. So that's something to think about. Or do we skip this middleman right here, this CRM, because this CRM is not a dual contact item, but this is, this is right here. but if something got, burned on here, we would be able to hit the safety relay, or we'd be able to hit the E stop here and bring this down. So remember, now it's getting dicey. We've got stops and we've got E stops. They're different. Stops are single channel, E stops are dual channel, but we still got the CRM. I like it. But if we get rid of the CRM and we just have this instead go to the output module, okay, that's what this is showing here. We just take my voltage and I instead pass that 13 and 14 safety relay to the output module. Well, that way it kind of doesn't matter if the CRM is up or down. The CRM could, let's get rid of this right here. The CRM is still up. We still got power. Everything's, running good. We just brought down the PLC output module because the voltage is being delivered to the output module. And so if you got 16 outputs, you brought it down. And so that's clean as well. Just depends on what you want to do. You want to bring down CRM and everything, or do you just want to bring down just a single output module? Maybe you got rows and rows and rows of output modules. Maybe you just want to bring down one. Okay. And then the other way to do this is have the voltage just bring down a single output. And so in this case, we would keep the output module with voltage, and then this would just bring down a single output. Let's say this was output 1. We would put the safety relay there, that module 13 and 14, and let's say this was going to the motor starter there, right? So bringing this down just brings down a single output, maybe the dangerous one, but all these other outputs, they're going to still work because they don't have the safety relay on them. So what did you do? I think a lot of people did this. I think they brought down the module right here. They put the safety relay here and they brought that down. And that's pretty common. I think you'll see that a lot. Bringing down an individual one, I don't know that you'll see that as much. You can. And also just bringing down the master control relay as it gets passed through the CRM. I think you'll see that a lot. Okay, so this depends on and what you're looking at and how complicated your system is and what you want to bring down. So hopefully that makes sense. All these different ways of how to incorporate the safety relay, right? Individual device, entire output card, or just the MCR, right? Safety contactors. So the safety relay needs to directly bring down the safety contactors. Does it? Does the safety relay need to directly bring down the safety contactors? It does. So how are we going to bring down the safety contactors? And so the safety contactors were 2 outputs, okay? They were 2 outputs on the card. So right here we had, safety contactor 1, and we had our safety contactor 2. They were 24-volt outputs. So we want to bring down those safety contactors. Well, we're just back to what we talked about a minute ago, because you have to turn on 2 individual outputs to turn those on. Well, bring down the card. They're both going to go off, and that way the safety system is working here. You want to bring down the MCR. If you bring down the MCR, that's going to bring down power to the whole system. So if this CRM provides voltage to the output card, well, then it's going down, and this isn't here anymore. It's just it's used up here, so it's kind of bringing down all of the IO. That works too, but somehow this has to bring down those safety contactors. So a lot of times when we draw this, we're showing here, K1, and we're showing here K2, right? Well, where's the voltage? Where's the voltage coming from here? Is it coming from the output module, or is it directly, wired? When I'm with the PLC, we're probably turning these on. So this, how are you breaking that voltage? You're just breaking the card. I think that's what a lot of you did, and you could do it that way. And then going back to here, when we had the safety contactors, we were doing the dual monitoring of the safety contactors, K1 and K2, to be sure that they were in the state that we wanted them to be in before we were turning them on, right? And then see what else do we have for the safeties. Oh, we had the overload. Okay, that's a great thing too. So these safety contactors were wired through an overload. The actual power circuit, the three-phase, starts running through an overload. So what are you going to do with the overload? And the overload is going to be an input on the PLC. Yeah, and that doesn't have anything to do with this right here, that overload. But maybe you use the overload to, I don't know, did you use it to bring down your system? You know, that overload brings down the system, everything dies, because that was the main conveyor on that. So maybe you had that overload bring down your system and everything died. You had to fix it, replace the motor, you know, whatever. And then you could bring that overload back online and get it cleaned up. Or we're using that overload to, I don't think anybody was using that overload to trip the safety relay, but I mean, I guess you could have. It's not really a safety rated contact on that overload though. It's not really made to come down here and bring this down. So maybe the best way is to just use that overload contact to bring down your PLC program. That overload, once again, is not part of the safety circuit, the safety relay circuit. Hopefully that makes sense to you there. It's good for monitoring. That's what it is, monitoring by the PLC. All right. We did machine safety. We talked about the difference between performance level and safety level, safety SIL, and all the acronyms that went with it. You know, what level of safety did you incorporate into the car wash? Because probably when that car wash was designed, it didn't have much safety in it. Like you just turned on the motor starters, and they didn't. If it was old and being refit, they probably didn't utilize safety relays or safety PLCs or dual channel e-stops and all that. So, you know, what safety did you put into that? Because we were putting in, you know, the monitoring, we were monitoring the contactors. We had dual channel safety. It was an uncontrolled stop, things like that. You know, that was like a PL3 that we were kind of putting into that car wash. And was this level of safety necessary? Well, that's what you just got to figure out or ask when you're trying to put this together. Due to the extra cost or the extra effort to make the system safe, hey, if this car wash was running before and it didn't have any safety features on it and only had stop buttons, was that okay? You know, it ran for 20 years before, and now we're refitting it. We don't need to make a PL5 or an SIL safety level 3 or 4 here on this thing. It does, you know, probably not. But maybe it is a good idea to put a little bit of safety in there, as long as it still works. So that's some of the things you got to think about when you're doing that. We talked about the different safety standards, just like all of our other electrical stuff. There's a variety of different agencies, excuse me, that would have a lot of good reading about what you might want to do. All right, and I talked to you guys in class that somebody's the safety engineer. You know, I mean, maybe it's going to be you. Maybe you like reading and trying to figure all this. I'm certainly not the expert, but there's stuff to keep in mind out there. All right. Homework review. So we did the high pressure gas application. So got a variety of different answers here. You know, we had, and I just wanted to hear your explanation for these. Like I think one of the answers was, hey, this is like they put this on a tank in the middle of Texas without anybody within like 100 miles from here. You know, that's kind of what they were saying. So, you know, they said severity of injury. So they said slight, normally reversible injury. And yeah, I don't totally agree with that. If this gas pressure vessel fails, even if there's nobody around, that's not saying that if somebody was around, you could be seriously injured. But they were saying, yeah, nobody's around. It's very seldom that, you know, as a matter of fact, it never happens, and there's nobody around. And so they just said start 11111, and they said as the required performance level of A, just because it was in the middle of nowhere. Now, I don't totally agree with that because if you just happen to hit the lottery and you're the one around there when this high pressure gas fails, well, then you probably got a possibility of a serious injury. So therefore, you're already headed down to C, D, or E, okay, S2. And then you start talking about what's the frequency, and you can make an argument that, hey, maybe this is in the middle of nowhere, or it's not really highly monitored, so you're not really around it. So maybe here, and then a possibility of avoiding the damage. Once again, it's probably under specific conditions, you probably can mostly avoid it. And so, a lot of people were coming in here with, something like a C or a D, all right? But some people, I think I got an E on here. They wrote it all up that, yeah, you're working around it all the time. It's super dangerous. It explodes. You're going to die. There's no way to avoid it, and described it all up and gave an E. So I was just kind of, there wasn't enough information on there to really describe where, when, how, what this application was. I was just kind of asking you to think about it a little bit. And this performance level then dictates, what kind of safety rated components and what kind of safety rated systems you need. So on the lab review, we did the mapping of the inputs and the outputs. Everybody mapped the inputs, all right? I didn't see many people mapping the outputs. In the last lecture, I talked a little bit about why if you would want to map the outputs or not. If you're not sure the way that all got broken down, watch that part of the lecture again. But not a lot, and it probably works, right? We did a good job of using subroutines and scheduling. So the system bit is interesting. Where do you want to put the system bit? A lot of people put the system bit into just the main, and then the main then contain all of the scheduling, unconditional scheduling of this, okay? And then you got to be careful with your conditional and unconditional scheduling of items. So here's what would get you in trouble. If you had, it would be a safety relay, a start, and then a bit, your system bit, holding here, right? If this was your main, that somehow the safety relay was what broke it, but you hit the system start and you got the system bit. And then in your main, you did this, bit, 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 and then you called your, JSR1, your JSR2, and your JSR3, where you started calling your subroutines, but you could only call them if the system bit was on, which you think, well, that's a decent idea. Well, remember a couple things. If you unschedule this if you schedule it with a bit and then you unschedule it, that doesn't really turn off the outputs in the JFR. Anything that was on when you unschedule it remains on. So this is not controlling the logic in the JSR. It's just unscheduling it. And so I don't really recommend doing this. I would recommend inside of this JSR, you would have your bit, your system bit, and then, whatever logic you've got going from there on, your system bit could activate that, what's going on in there. But I would probably make these unconditionally scheduled just to organize your information. And that's what we did in the lab. You didn't need all those subs, but I just wanted to get a little practice doing that. And so how you incorporate this was okay. So some people took this right here and they put it in its own subroutine that, unconditionally, that was their a JSR system. And they just moved all the system and the safety stuff kind of into there. We'll look at this a little bit differently when we start using the safety function of the safety controller, all right? Blake program template. I think some people might be doing this. Just remember that I got a lot of stuff coming in and out, so we're always going to be using the bridge. Maybe you could use the hardwired digital inputs, digital outputs. There's analogs that are hardwired, and if you just want to keep your PLC in the same spot every time and keep your bridge in the same spot every time, you could make a little bit of a program template, save it as PLC3, and then when you start do save as lab 3, save as lab 4, save as lab 5, it might save you a little bit of time to if you got a blank program template. Okay. We also talked about just saving everything as you go onto the processor, so you have a backup of everything. I don't know if that's a good idea. You could do it, actually. We talked about inhibiting tasks and programs and everything like that, and it would kind of work. The UCIO being the issue if you had to inhibit it. You do want to bring in a flash drive, I think, because the way these computers are and they're going to get redone here one of these days. I think you should have your programs on a flash drive to back it up. All right. So we're going to be utilizing remote I/O in the lab. Some people are basically already done with this and they're getting the hang of it. And we covered this in the prior class, and that's the Ethernet point I/O. And we're going to talk about using the local rack and the remote rack, and then we're going to talk about produce and consume tags, Boolean versus DINT. Okay. So when we talk about remote I/O on inputs or outputs, or I guess local input, because sometimes you could have two processors in one rack, I guess, but you can read the status of an input. Let's say you have an input card. Okay, you got to input and push the button. You get a light on it into two or more controllers. So normally we just been pushing the button and we've been reading it into our controller. Hey, the input's on. Well, two controllers could read the status of that input. You could have that input card on multiple controllers because the input is just the start of the scan. It hasn't solved any logic or made anything. So go ahead and just like we use an input multiple times in a program, you could use that input multiple times in multiple programs on multiple controllers. Okay, hopefully that makes sense to you. It's probably not life or death. Just want to be sure that you understand where the I/O is coming from. You cannot read the status of an output into more than one controller. Well, that's different. So if you have an output card in your rack and multiple controllers, you don't want to have the program in one of the controllers turning on an output because maybe it's a dangerous output, and then you've got a completely different controller, and it could be on a local rack or a different controller on a remote rack, controlling that same output, because one of the programs or one of the controllers might be trying to turn that output on, and the other controller might be trying to turn that output on when you really want it on, or you might really want it off. So it's probably not a good idea, or you can't do it. So just be aware of that, right? Some types of I/O switches output wires are owned by the processor. So once you set up an I/O and then you download it, and then you run it, that processor is going to own that output card, for example. Okay, and then so when another processor tries to download and it says, hey, somebody already owns that card, I don't get use of it. Okay, and so that's part of the lab is setting that up to show you exactly how that works. And so one of the things that we use to kind of get around this in sharing information between controllers is produced and consumed tags. And it shows here a logic controller produces and consumes tags. So you could have a controller right here producing data and a tag, and then three other controllers on the network could be consuming that tag data. Now remember, if it's just an input card, these controllers can read the status of that input anyways. But if it's something more than that, maybe it's a counter value, or maybe, I don't know, whatever, anything that you can think of, maybe these different PLCs want to know what kind of data this PLC or what kind of tag this is creating. That's called a produce and consume tags. Now, I've got a lot of information. I got a wonderful article on the D2L that I want you to read about all the produce and consume tags. That's kind of what the quiz will be over. So you're going to want to, dig into that produce and consume tags, Alan Bradley. And the other thing I'd like you to do is you're going to have to, stop this PowerPoint and look at this video. Look at this PowerPoint on D2L, and then click this link right here: produce and consume tags. It's a little bit of a video about 5 minutes, I don't know, of how to make produced and consumed tags between two controllers. So if you watch this on your own, then when you come to class, you'll probably have to watch it again. But you can do this produce and consume tags. And then when you get to doing the produce and consume tags, a lot of times what I like to do, if there's enough room, is I like to split my screen here, and on one side I might have a Logix program running, because this case would be having a 24 running, and on this side having a 37 running, and then you'll identify one is the producers, one is the consumer, and you can go back and forth and be sure and make the tags and everything like that. Okay. The thing is, if you're just doing it on a single screen, then you're going to have a couple of instances launched down here, and you're just going to have to keep going back and forth between them. But if you watch this right here, you'll kind of get the idea of what's going on with produce and consume tags. Okay. And you'll learn, and then in the literature I got for you says a produce tag cannot be a Boolean. Okay, other types of tags are ideal for this. A user-defined tag could be a great item for produce and consume, because a user-defined tag could contain a Boolean in it, right? So we're going to do user-defined tags later. Okay. But we can consider it a 16-bit word. There's a one where one is indicating the least significant bit is true, okay? And this would be a integer. You can quote, I got here, replace a bool with a dent by specifying to the bit level. So if this tag right here was called PB status bit, this would be PB status bit .0, .1, .2, .3. So if we read in this word or this register right here, and we read it in at the bit level, then all of a sudden we can share this data. And so we can check the status of I guess a bool. We're kind of tricking it here. We can check the status of this single bit by reading in a word at the bit level. Okay. Network transmission. So for two controllers, which is what we're going to do to share tags, they must be in the same backplane or attached to the same control network. We're doing Ethernet IP, and we're using the same network. We're doing 192.168.1. We're using a .1 network, all right? So we can do produce and consume tags. Produce and consume tags can be bridged over two networks, such as a .1 or .10, but Rockwell Automation doesn't really support that idea, but it's going to work. And we might get into it where we'll produce a tag and share it between a bunch of controllers on different networks, all right? And so when we get into safety PLC, guard logic situations, that guard logic might want to, it's going to be on its own network, right? But if there's some other stuff out there that we want to share between all the zones or all the VLANs, the safety PLC situation might be completely different here, okay? And we will later on get into safety PLC, the guard logic. That's why we got it, okay? RPI considerations. Chapter 2 is produce and consume literature, and the detail talks about your packet transfer rates and all this, talking about that these refresh rates need to be set, the same. They do some calculations on, large array of data coming through, and I want you to take a look at that just to see that when you're producing and consuming these tags, speed definitely becomes important to be sure that you can broadcast and listen and talk and listen and talk, listen as you're supposed to, and that you don't miss any of the data, or if any of the data that you're sending is too large, that it's getting truncated or something like that due to not enough time. So there's chapter 2 is you're going to take a look at this, and we can talk about it a little bit more, but there'll be something on the quiz about that, about how it works, right? HMI panel view. We're going to start using the panel views again, and we did that last time. We're going to go ahead and try and update FactoryTalk View to version 15. Because right now I think we got 9 on there, 9 or 10, and it does not work with version 32.7 of Logic. I think 12 goes up to 32, and we're below that. Remember, the old ones were on 24. So we're going to update the fit to version, the latest and greatest of panel view, and hopefully that works well with the guard logics running version 37. We might have to update the panel view firmware because right now we compile to runtime 7. We might update the panel view firmware so that we can do a different level of runtime and get it all working. My note here is prepare for a rough ride here. This might be a little bit of a learning activity. Going out there on the internet and taking a look at forums and stuff, it sounds like it's been a bit of a rough ride for some people. And then when we go to Windows 11, that ride becomes rougher. But we're going to get it working. That's because that's what we do. That's what controls engineers do. They get stuff to work. All right. You have some Ethernet port I/O. We've got some information from ELTE261. I can produce that for you again if you need it. But when you go to set up that Ethernet port I/O, you might have to match the remote chassis, and that's the feature and logics. You want to be sure that your rack size is correct and that the children, and then you got to match that that rack to what your logics program says. Sometimes, every once in a while, it'll take it, doesn't need it, but otherwise you got to go into the features and match remote chassis. Okay, so that's kind of what I got. Take a look at the lab. I'll open up the quiz and watch that other produced and consumed tags video.